righty, folks, have another one of these interesting problems where we're supposed to find all possible or count the number of integer solutions. Now, they give you a big hint here. They're telling you that there's 16 integer valued solutions. And so it says, it doesn't necessarily say to find them, but it says to verify there are exactly 16 of them, okay? Now, the form that it's in right here, it's almost impossible to do, because what would you do? Just guess and test? What would be the terminate condition? How would you know you were done? All right. So there's this fantastic little idea that allows us to factor this. And it's kind of like completing the square, but some people call it completing the product. And if you'll notice what we do right here, I recopied this in an equivalent form. I just brought everything over. It's usually a good idea to get 0 on one side of the equation. And this idea just works, you know. We know that we need the terms minus 11x and minus 8y, so we ensure that happens right here, right? You have minus 11x minus 8y. But what happens is that throws out a term, another term. Let me mark that in here. See what really happens, what's really going on here is you have minus 8 times minus 11, which is 88. And so the constant term here would be plus 88. Would be plus 88. But notice that when you subtract minus 105, see, we still have equivalency here. In other words, we get what we want. We get all these terms that we need. We need to retain this constant term to maintain the equivalency. So this 88 is kind of the price we pay, and we had to subtract off 105, and that's very similar to the complete the square, but we call this complete the product. Okay, this is called complete the product. Complete the product, I think it's called Simon's favorite factoring trick at the University of Maryland, but we're actually completing the product here. All right, it's kind of interesting, not complete the square, complete the product. And again, I've seen it called, I'll just abbreviate this. I've seen it called SFFT. And that's just kind of some playful banter going on between some students at the University of Maryland, I think. Simon's favorite factoring trick, or theorem if you want to be more sophisticated. All right, but you see, we've got this down to a very manageable situation now. We can find all the solutions because we have a factored form, which is much easier to work with from a standpoint of guessing and testing, if you want to call it that. Now, the big observation here is that 105 has exactly 8 divisors. And I've written them down right here. 1 times 105, 3 times 35, 5 times 21, and 7 times 15. Now this is going to lead to 4 cases, and what gets laborious about this is that it's not enough just to equate it. I picked 5 times 21 kind of arbitrarily here, so I'm using this as our example. This will be one of the 4 cases. But notice, folks, it's tempting to just go, okay, call this 5 and call this 21, solve for x and y, done. But you see the same holds in reverse. You have to reverse it. And moreover, since a minus times a minus is a plus, we have to write it with these minus signs here. So you can see what we've done. This is tedious, but at least it's a schema that will have a terminate condition. So if you notice right here, 13, if you put 13 right here for the x, okay, there's 13. 13 minus 8 is 5, and also 32 minus 11 is the 21, and all the rest of these you can check them out, okay? But the key result here, as far as the way this question is worded, is in this is one of the 4 cases, and it produces 4 solutions, right? So what's clear without going through all the laborious, onerous, tedious calculations is that the other 3 cases will add 12, and that means there'll be exactly 16 solutions. And you can generalize this, I think. It gets down to the number of factors of this constant term and all that. But to complete the product result is what made this thing fly. Let me know what you guys think about complete the product. Thanks.